Long-term potentiation can be viewed as a three-part process that involves first the induction, or the learning experience. This is when the LTP happens, where the NMDA receptor communicates with the cell's nucleus and creates the long-term changes. Then there's maintenance, which is the memory that gets formed, and every time it's recalled, we get the expression of it. So these are the three steps: induction, maintenance, and expression. Glutamate receptors are necessary for the induction. So small stimulations will trigger just the AMPA receptors. Remember, those are the ones involved in normal, everyday neural signals. They are short-acting. They don't produce long-lasting changes. But a large stimulation will trigger activity in the NMDA receptor. And that's because that large depolarization, where that neuron gets really excited and made extra positive, that ends up removing a magnesium ion that would normally block the NMDA receptor. So let's take a look over here where we see the AMPA and the NMDA receptor. The AMPA receptor is always open, ionotropic. When glutamate binds, sodium goes in, and it's going to relay that signal. It's going to bring those positively charged ions inside the neuron and hopefully create enough EPSPs for an action potential to happen. The NMDA receptor, though, is normally closed. It's not active in the normal everyday activities, but a very strong depolarization where tons of glutamate comes in will dislodge that magnesium molecule, opening up the NMDA receptor, allowing glutamate to bind. Sodium ions enter, but so do calcium ions. And that calcium that comes in activates these secondary messengers that then travel to the nucleus and tell the nucleus to make long-lasting changes. Activation of these proteins, these secondary messengers triggered by NMDA receptors, are the ones that lead to these changes. And what these changes are new AMPA receptors. These new AMPA receptors then are the ones that allow that neuron to become more sensitive to the glutamate that's going to come in from then on. In addition to that type of change in the postsynaptic neuron, where we get an increase in the number of AMPA receptors, we also see that there is an increase in the amount of glutamate that gets released from the presynaptic neuron. For that to happen, the postsynaptic neuron has to communicate with the presynaptic neuron, and the way it does that is in the form of a gas. So I'm going to make little bubbles here to represent this gas, nitric oxide. Nitric oxide acts as a retrograde messenger. In other words, it's a messenger that goes back to the presynaptic neuron, making that presynaptic neuron release more glutamate from now on. Research has shown that LTP-initiated growth of the hippocampus is involved in memory formation. In particular, London taxi drivers have been studied because they have to memorize the layout of a very large and complicated city before they can become taxi drivers. And they had larger posterior hippocampus volumes than non-taxi drivers. So this is a demonstration of how the hippocampus can grow as a result of life experience. And its growth comes about because of long-term potentiation. The difference in the size of the hippocampus was in proportion to how many years they'd been a taxi driver. So the more years they'd been a taxi driver, the larger the hippocampus, and this is associated again with more LTP. Now let's see a summary of how long-term potentiation happens. So once again, here's our presynaptic neuron. Here's our postsynaptic neuron. So information is flowing this way. We're going to have our always open and available AMPA receptors. In addition, let's put in a NMDA receptor. But the NMDA receptor, remember, is always going to be blocked with this magnesium ion. And we'll have our vesicles here in the presynaptic with the glutamate inside. And when the action potential travels down the axon through saltatory conduction and it arrives here at the end, remember calcium is going to come in. That's going to make the vesicles fuse with the cell membrane and they will release the glutamate. Neurotransmitter out there, and then the neurotransmitter cannot bind to the NMDA receptor because it's blocked, but it can bind to the AMPA receptor. Now, if this neuron, the postsynaptic neuron, is getting an additional input, that's also releasing all kinds of glutamate at the same time, we can end up with a very large depolarization. Here in the postsynaptic neuron. That large depolarization will then remove the magnesium from the NMDA receptor, and it'll allow glutamate to bind to this NMDA receptor. The NMDA receptor will allow sodium to come in, but also calcium. That calcium, when it comes in, is going to activate these proteins that will then go to the nucleus and create the new AMPA receptors. Allowing there to be greater activity at the synapse than before. And remember, there's also the release of the nitric oxide. In the form of a gas, which goes to the presynaptic neuron and tells the presynaptic neuron to release more glutamate. So next time it will release more glutamate. At this point, I would like you to take a moment and look at this worksheet to figure out how LTP works and give you a chance to review some of the things that we've gone over. You'll want to label the structures first, so the items that don't have a number. So let's see, the neurotransmitter and the name of the receptor that's involved in the induction of LTP, and the name of the receptor that's involved in normal synaptic transmissions. Go here. And then describe the steps highlighted in these numbers 1, 2, 3, and 4.